Welcome back to another lesson in Math 8. Here we are at Unit 2, Lesson 12. What we will be doing today is we're going to continue a little bit more of our discussion from Lesson 11, where we talk about using the equations for lines. The first thing that we want to do is we want to actually talk about dilation, just a quick review. We see that we have a dilation with a scale factor of 2 that sends A to B. This is really important information right here because it tells us the direction from where the ray is going. And so that ray we know is going to take A to B. Since that's our direction, we want to go ahead and recognize this from A to B. We'll go ahead and put a line right through that to indicate somewhere along this line we will find the beginning of our ray. Where is the center of that dilation? Well, when we think about the center of that dilation, that is where our ray begins. First thing we know is that if we're looking at this right here from A to B, we can think of this as one single unit from A to B. We know by a scale factor of 2 that distance would have to double. So let's go ahead and take that distance of A to B just here on a piece of paper, and we'll bring that distance back this way, create another point. And maybe we'll call that one point P for our center. The reason we know that it's right here is because if this is 1 unit, that means this is also 1 unit, and I double that distance. Now we have the distance from P to B is a total of 2 units, where each of these are 1 and 1. Quick review of dilation there for you. Let's go back into a little bit from yesterday of writing a relationship from 2 points. A relationship between 2 points is also a way of talking about writing an equation between the 2 points, but it's also talking about writing a rule between points. It's also talking about finding the slope between 2 points. So we're going to use what we know about similar triangles, and we're going to find an equation for the line in this diagram. What we know about similar triangles is that if we were to think about this part right here as a triangle from 5, 3 to 7, 7, and to go from 7, 7 to this other unknown point. We know it's just right here, but we don't know what it is. We know that these two triangles must be similar because number one, they have 90-degree angle here, and number two, we know that they are slope triangles, which means right triangles on the same line that covers their longest face. And right triangles, we know from our angle relationships, I can actually translate this triangle right here, and these two angles would be corresponding angles that are equal in measure. Same thing with the smaller one up above. That's great. One of the things we also learned about with similar triangles is that when you dilate their distances between points, we know that they're proportional to each other. One key thing that we can do with this is we can find the slope of their face, of their diagonal face. In this case right here, from 5, 3 to 7, 7, we could pretty quickly see that we have a rise of 2 and a run of 1. So our slope, we might see that really quickly as a slope of 2. We'll just put that on the side. Let's review what we talked about yesterday, though, or in the previous lesson, though, talking about lesson 11, where we had this slope formula, where we knew slope is equal to, get ready for it, y2 minus y sub 1 divided by x sub 2 minus x sub 1. And again, quick recap, how did we get these right here? Remember that the 1 and the 2 are strictly numbers for classification that come as an order. As we follow this line right here, from left to right, as we read the graph, we see that the line increases from left to right. And so as we follow along, 5, 3 is the first ordered pair that we come from. So this is ordered pair that has x and y 1. And then this is the second ordered pair we come to with x and y 2. As we understand those things, let's go ahead and find our equation for the line. What is the slope of this line? This is actually number 2. Let's go ahead and start substituting values in. I'm going to bring this formula down here. Y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. And then we're going to substitute values in here. So we see the ordered pairs of 5, 3 and 7, 7. So let's go ahead and substitute now. 5, 3 was our number 1 for 2. So we're going to go 7 minus 3 and then 7 minus 5. So the change in y over the change in x. And we go ahead and simplify. 4 divided by 2, or simply 2. Does this slope appear to be in your equation? Well, I haven't written my equation yet, but having the slope will really help. Let's talk about how we write our equation, or we write our rule right here. Remember, the equation for the line is also talking about our rule that all the points have to follow if they're going to be on the line. What we do know is that our slope is 2. That's really important to know because we know that our rule has to equal 2 by the time it's done. So let's think about that. We see that our line is not passing through the origin. Remember from lesson 11 that when a line passes through 0, 0 at the origin, we call that a proportional relation, meaning that all of my y values divided by my x values, so y divided by x, we saw gave us a proportional value that we could follow as a constant rate. When we see that our line is not passing through here, we talk about the slope and we find that slope, but we use it with a little bit of this proportionality. To get that proportionality, recall that we took a single known point and we would translate that point back to the origin as part of our rule so that this would hold true. Since we know what our k is already, that it's 2, or our slope is 2, let's go ahead and write our rule. Remember this section from right here, this would indicate y minus 3 because my y coordinate is decreasing by 3 units. So that becomes my numerator. And then my x coordinate is going to go from 5 to 0. So this would be x minus 5 for my x coordinate. And we see our rule is written now. I could take this a couple steps further by multiplying the denominator to get just a single line, no fractions in it, but we're not going there yet. This is sufficient enough. So now what we can do with our equation for that line is we can start testing other points to see if they fall on that line. I would recommend to always test this to make sure that it works for at least 2 points on your graph to make certain that you have the right equation. So knowing that our slope is 2, rise 2, run 1, I'm going to use a different point than the one that I went ahead and moved. And we're going to find this one is 6, 5. Let's go ahead and test that one just to make sure, and we'll use 7, 7 just to make sure our equation is right. So when we have 6, 5, we want to substitute the 5 for the y. 5 minus 3 divided by 6 minus 5, which is equal to 2 or 1. This does check out. Let's talk about the other word pair, 7, 7. We take 7 minus 3 divided by 7 minus 5, which is equal to 4 halves, or 2. This one also checks out. I know for a fact now that my rule, my equation for the line, is definitely correct because when I go to substitute known values on here, those solutions make this equation true. So now let's test it for these other ones. 9, 11. Let's go ahead and substitute. We use 11 for the y. 11 minus 3 divided by 9, which plugs in for the x. 9 minus 5 is equal to, and it needs to come out and simplify to 2. 11 minus 3 is 8. 9 minus 5 is 4, or 2. Is this on the line? Well, yes. Since 9, 11 makes my rule true when plugged into this, following that change in y and the change in x, and we get a slope of 2, this comes out to a true statement. So 9, 11 is also on the line. Yes, it's on the line. How do I know? Well, because of what I just said. When I plug it into my equation, it follows the rule of proportionality for this line. Let's talk about 100 and 193. Substituting these values in, 193 for y minus 3 divided by 100 minus 5 is equal to 190 divided by 95. That's pretty big numbers, but if I understand this right, by a scale factor of 2 means, or excuse me, by a slope of 2 means that 95 times 2 needs to equal 190. I know that 90 times 2 is 180, and I know 5 times 2 is 10, and 180 plus 10 is 190. This does equal 2. Yes, this ordered pair of 100 and 193 is certainly on the line because it follows the rule. So let's try something. It says there's many different ways to write down an equation for a line like the one in the previous problem. So with this one right here, there's actually a lot of different ways that we can write this rule. I could have used this point over here of 7, 7 and written my rule as y minus 7 divided by x minus 7 equals 2. That's another possibility, and that's okay. What we are going to do is see if these other ordered pair, or these other equations are also rules that can represent this line right here. So we know that the slope has to come out to 2. So let's go ahead and take 5, 3, and 7, 7. I'm going to go ahead and put these over here. I have the pairs 5, 3, 7, 7, and a slope of 2. And we're going to verify if these 2 points come out true in here, here, and here, then these are valid equations for that line. This one looks promising because I see that the slope is equal to 2. Let's go with 3 minus 3, and I already recognize I have a problem. And then 5 minus 6. I see that the numerator actually comes out to 0, which tells me that no matter what the denominator is a 0 slope. This one doesn't work. This does not represent the line. I look at the next one, y minus 6 divided by x minus 4 is equal to 5. This is not the correct slope of 2, so this is a no. The slope is not accurate, so it just won't ever work. When I look at the last one, let's go ahead and start with that 5, 3. We're going to substitute 3 for y, 3 plus 5. Oh, and I'm just jumping into this one because I see that the slope is 2. And then we'll substitute x, 5, and 1. And I see that this is 8/4. That's good. Let's check one more just to be sure that it's not an anomaly. And we will go with this. 7 plus 5 and 7 minus 1 equals 12/6, which is also equal to 2. This is good. This one right here, yes, this equation is a good rule. Explain your reasoning. When I substitute 2 known values, 2 solutions for the graphed line, and they come out true, then I know that that equation works. When I substitute and one of those solutions doesn't work, then we are not on that line. And when the slope is different, I know we're not on that line. Okay. 12.3, dilations and slope triangles. Remember that a slope triangle has this in common. All slope triangles have a common side, or excuse me, their longest side right out here always follows a common line. And that line, that slope, will constantly be true. The other thing that we have is all slope triangles have to have right angles. So if it has a right angle and it shares this side, we know that those triangles are similar. So let's go ahead and dilate some triangles. This says draw a dilation of triangle ABC with centers 0, 1. Whoops. 0, 1. Notice that it's not 0, 0. That's okay though, and a scale factor of 2. Well, let's go ahead and use our side lengths to be able to dilate. If this side length is 2 units, by a scale factor of 2 would be 4 units. We're going to call that B prime. So out to here. We also know the vertical side right here is 1 unit tall. Doubling that scale factor, or with the scale factor of 2, would make that 2 units tall. And what we notice here is that we're right back to that line that we drew earlier for, I'm going to call that one C prime. Those are really hard to see, so let's do this and hope that I don't make mistakes with my pen. So let's go ahead and try this one. Scale factor of 2.5. Well, if my triangle, when we're talking 2.5, if we look at this one, 2 times 2.5, when we're talking about the distance of AB, we know that AB prime, we'll call it double prime because the new spot is going to be twice, or 2 times, 2 units here, 2.5 times longer is going to be 5 units. So B double prime will come here. And then we talk about the distance of 1 right here, that this distance of BC, and we want to multiply that by a scale factor of 2.5. Well, I know 1 times 2.5 is 2.5. So I come up 2.5 units. I know that it's going to be right here because of my ray that follows out. C double prime, and I see a triangle. We could see that same pattern if I continue to follow it, working all the way out. So the question is, where C is mapped by a dilation with a center of 0, 1 and a scale factor of S, where is C mapped by a dilation? When I don't know the scale factor, let's look at this from another route then. Where is C mapped? Meaning, how can I tell, like, how are ordered pairs affected? That's kind of what we're asking, or how are the X and the Y coordinates going to be affected by this dilation? Well, let's look at those ordered pairs. We go from 0, 1 out to 2, 2, out to 4, 3, and then on to 5, 2.5. Let's see if we can come up with a rule for this. Let's take a look at just our X coordinate. This one's kind of funny. It's not quite following through with the other one. So I'm going to look out my line here. If I were to dilate by a scale factor of 3, I'd end up here. That would be 6, 4. Let's use 6, 4. I think that's a better way to do it. And let's look and see what happens as we go. We see that we go from 0, 2, 4, 6. So I'm increasing by a rate of 2 each time. But I think more importantly, what I see with this is that by a scale factor of 1, we don't move. By a scale factor of 2, I double. Scale factor of 2, that doubles. A scale factor of a scale factor of 3 times 2. It looks like whatever happens, anytime that I take the X coordinate and I multiply twice the value of the scale factor, I get this. So 2 times 0 is 0. Back to the center of dilation. 2 times 2 is 4. My distance from here, right? 2 times the scale factor of 3. So twice the value of the scale factor of 3. There's scale factor 1, 2, 3. Gives me an X of 6. So I know for a fact that all of my X coordinates would just be twice the scale factor. Let's look at what happens with the Y's following that. We go from 1, 2, 3, 4. It looks like under the scale factor, I just take that scale factor and add 1 to it, and that's how my Y's will change. So now with the question of this, for which scale factor does the dilation from center 0, 1 send C to 9 and 5.5? Well, we know that under dilation, we're going to have similarity. So the question is, what's the dilation from here out to here? I think probably our easiest thing that we can do is we can look at that and we can say, what scale factor takes this distance out to here? We could sit there and measure it all out, or we can look at the distance from here to here and try that. Or we can look at the distance we can look at this distance from here to here, because we're talking about similar triangles. So we are going from 2 out to 9, and we are going from 1 to 4.5. So if we're growing, those ratios won't work, so I can take the reciprocal and take 9 halves to show growth, because I know that my scale factor has to be greater than 1 for growth. And I see 4 5/10 over 1, and actually these two are equal. I know that my scale factor must be 4 5/10, because look at this. The change that we experience right here is going to take us from 1 unit to 4.5 units. That's 1 times 4.5 is 4.5, and 2 times 4.5 is 9. We are proportionally larger where we should be, and we are proportionally working those values. And I think the one spot where we can see people make a mistake is sometimes they'll go from the bottom here and call this 5.5, which would actually be the wrong height of the triangle. We need to pay attention to the actual height of the triangle as it is similar to the original triangle. When we work with this, to close this all out, we want to talk about this, what we can use, or we can use what we know about the slope to decide if a point lies on a line. And here is a line with a few points labeled. The first thing we want to do is slope triangle with the vertices 0, 1, and 2, 5 gives us a slope of 5 minus 1 divided by 2 minus 0. Remember that when we see these points and we see this right here, this is coming from the slope formula. Slope is equal to y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. This being the first ordered pair that we see, ordered pair number 1. This one, ordered pair number 2, coinciding with the subtext. And we see right here, 5 minus 1 over 2 minus 0 to equal 2. When we know the slope, we can use the vertices of 0, 1 and x, y to give us a slope of this. From here to here, if we just translate down 1 unit, that's decreasing our y coordinate by 1, not changing our x coordinate at all. The slopes are equal to 2 because these two triangles are similar. And then we get an equation that's here. We can check whether a point 1123 lies on the line by substituting our x and our y into the equation. So 23 minus 1 divided by 11 is equal to 2, which is absolutely true. So this is a solution for the equation because it is on the line. Thanks for hanging in here for another lesson. I hope that this was helpful. Please go ahead and feel free to give me your feedback. And I hope you have a great day. Don't you give up on this.